Okay, so I just want to spend a few minutes to review our chapter 9, and then we'll move on to chapter 10. So from chapter 10, I think we're going to take a little bit of slower pace because if you recall, when we started looking at BJT and MOSFETs, chapter 5 and 6, those two chapters are not going to be on our final exam. So our final exam starts with chapter 7. There's a small signal model. So we look at basically the pi model of MOSFETs and BJTs. And then we also talk about the T model. And we also derived how we get from pi model to T model. And also we discussed where to use the T model and where to use the pi model. So basically, if you have a common source or you have a common emitter amplifier, you can always use the pi model. If you have a common gate, common base, or you have a common collector, or you have a um, um, common drain amplifier, you should always use this T model to make it easier. And then if you have a common source amplifier, for example, but you have a resistor at the source, even though the common source is not strictly common source, but sort of common source, but you have a resistor. And T model also is the best. And by using T model, we can observe the gain by looking at the input resistance and output resistance because the two voltages are basically proportional to each other, right? So that's fairly easy to think about those models. So those small models are really foundations of the whole thing here. The small thing, whether it's pi model or the T model, to get familiar with those two models are critically important. So that's why you see them often here and there and so on. And within these models, you have two parameters that are very important. One is to calculate GM for both BJT and the MOSFETs. How do you calculate GM? For example, for MOSFETs, GM is 2 times ID divided by VOV. You just got to bring that bill. You don't have to go back to look for that equation, flip over 100 pages to find where the equation is, and you might find the wrong one because something that it's not what you were looking for, right? For the BJT, for the pi model, there's R pi. And do you guys remember how to calculate R pi? So R pi basically should be voltage divided by a current. So the early voltage divided by, it's beta over beta divided by R pi is beta divided by IC. And then we also constantly looking at RO, the early resistance or the internal resistance. So RO, equation for RO, you should also memorize for both MOSFET and BJTs. So for BJT, for RO, for MOSFET, for example, is VA divided by ID, and for BJT is it's this V divided by this IC, VT divided by IC. So I'm sorry, VA divided by IC. So all those things, they come together with this pi model where you have GM, you have R pi, and you have RO. And then also, of course, from R pi to RE, there's a better ratio, right, for that model. And also for the MOSFET small signal model, at the source side, if you use the T model, there is a resistance there. So that's something also to remember, right? So once you get that all set up, and moving on from chapter 8, from chapter 7 to chapter 8, we are looking at this current mirrors and current source. The reason we do that, because we don't want to use resistance. That's one reason. We want to use everything, the biasing circuit, by a current source, which make your amplifier, make your IC design very small. and compact. Another reason is that with amplifiers, we always have some sort of load. And in the beginning, we always have a resistance at the drain or resistance at the collector. That's your load resistance. But later on, as we said, we don't want to use that resistance. And what do you use it? And you use another current source. When you have a current source, basically you have this RO of that current source becomes your load resistance. So that increase your gain and eliminate the use of that resistance. So that's why you have a current source. Because the idea of current source increase the gain, so you eventually say, well, if we want to further increase the gain, we can simply increase output resistance of these current mirrors. So that's where it comes to cascade amplifiers. Well, we can double the gain, or not double. We can actually, what do you say this? It's a square of the original gain. So your original gain is 25. Now it's 25 to the times 25. So it's a square, right? So that make your gain increase dramatically by using this cascade amplifier. Okay, so chapter 8 basically just that's that simple. And we also did talk about this Widler and Wills current mirrors. Those are very smart designs, which helps to make your IC even smaller and smaller. So those are the really neat stuff to do. But then from chapter 8 to chapter 9, we said, okay, well, you can do amplifier, you can increase the gain, but sometimes our sensors do not have a ground by itself. Like we talk about this string of battery voltage measurement. If you want to measure voltage of the cell in the middle, you don't have a ground. So between these two, we call it differential. So we take the differential output, we'll put it to a differential amplifier. And so that's where differential amplifier comes from. You can use BJTs, you can use MOSFET to build a differential amplifier. The gain of a differential amplifier basically is the same as a single-ended amplifier because your input is reduced by half. So basically it's the same gain. Now the other difference is that for differential amplifier, because we take output from one transistor instead of another, so we take between these two, therefore we are able to get a positive output instead of negative gain. So the output can be positive. So then we move on saying, well, for this differential amplifiers, what happens is that if you have a mismatch in your circuits, whether it's gain mismatch, transistor mismatch, or resistor mismatch, your output is going to be different, even though the input is common mode. So now you got to, okay, well, we have to find out what is the common mode gain. When the circuits are perfectly matched, your common mode gain is 0, but it's not perfectly matched, there's a gain. That gain divided by this differential gain, or differential gain divided by common mode gain, that's called common mode rejection ratio. The bigger, the better. Okay, your common mode gain becomes small. So that's how you get your common mode gain. And similarly, you can also use cascade, you can use current mirror load to increase your gain, to reduce the use of resistance, and so on. Okay, so that's your differential amplifier. Then within that same thing that we talk about the range, like input range, output range, because you have to maintain these transistors in saturation region for the MOSFETs or in linear region for BJT. That will limit your output and your input. And for MOSFETs, we had examples showing that your input can be as large as the input as the voltage supply. That's called real to real. So we got this common mode range, and we got this common mode input range, common output range. So we talk about those. And then we say, okay, single stage, sometimes it's not good enough. The gain is not as big as we like, in the tens usually. They will want them to be in the hundreds to thousands. What do? You can add stages. So from one stage to another stage, you use them in series, so your gain dramatically increases. And also, in order to make use of the output, we have to convert this a double-ended output to a single-ended output. So that can be done by shorting one, like a drain to ground, or we can use a current mirror to realize the same function. So then that's what we have. So now you put them together, it's actually not bad, not so much. But the process, of course, is very complicated because there's so many equations to derive, right? So there's one thing I said in chapter 9. I said, let's skip the offset current for now, and I want to revisit. Actually, if you look at this offset in this differential amplifiers, it's not that bad to understand. The reason is this. Ideally, when the circuits are perfectly matched, if we ground the two inputs, what do you think output do you get? Whether it's DC or AC, whatever. If you ground this input, what do you get at the output? 0. If a circuit is matched, it's 0. But the problem, if the circuit is not perfectly matched, what happens? Let's say your circuit slight difference in terms of W over L, then you're currently starting more on this side, and then this side, what do you have now? So if current started more than over here, the voltage ID1 is, the voltage at this output is slightly less than the voltage over here. And then the voltage between these two terminals are no longer 0. That's called a DC offset. So DC offset happens in any amplifier. It's just so small that in many applications, we don't care. Like it's usually in the millivolts. Usually in the millivolts. But the problem, of course, if your input is millivolts, you have a gain of 10 to a couple 100, and then your output is a few millivolts, it's not a big deal, right? Because if your output is 2 volt, let's say you got 2 millivolts DC offset, you probably don't care because it's less than like 0.1%, less than 0.2%. It's not a big deal, right? But sometimes if your input output or your output is so small and your DC offset gets so big, let's say your output is 100 millivolts, that's what you want, but then you got a DC offset of 10 millivolts. Would you care now? You do, because the 10% error is introduced. So, okay, so we know there's an offset. We also care. What do we do then? Well, it's actually very simple. Because there's this offset at output, if we apply some sort of voltage at one of the gate, you see what happens? Let's say, for example, if output at 2 terminal is lower than this one, and if we increase the voltage over here, the voltage here will increase. Until this voltage is same as this voltage, we're done. So no more DC offset. So the idea to remove DC offset is to apply a voltage. Because VCM, we call it VO, we call it VOS. And then when we apply this VOS with the DC voltage, you see that it's this DC voltage, positive terminal over here, it's going to increase the current, so the voltage here is going to reduce. And the negative terminal over here is going to reduce the current, so the voltage here is going to increase. So, and then eventually this will become the same. So ideally, we want to apply just really, instead of 1 voltage, we can basically apply 2 voltage source. And we apply like half, maybe minus half VOS, like times minus 1, and this we get plus 1/2 VOS. So basically plus 1/2 here, 1/2 here, and to balance the voltage. Now this sign could change because we don't know which one is bigger, which one is smaller, right? For example, if you have RD1, RD2, you really don't know. So if RD1 is too big, this may be positive and this is negative. If RD1 is smaller than RD2, then this becomes negative, that's positive. So when you design the circuit, you always design a small DC offset, like between these 2 terminals. It could be positive, it could be negative, it could be 0 if you don't need it. But what the idea is that bring this DC output at the common mode to 0. And then at that point, you can start to apply your small signal. So make it easier. Okay, now the question is that how much should we apply so that we'll get a 0? Well, it depends on the mismatch. So basically, if you look at let's make some assumption. Let's assume that RD1 is equal to
RD plus third RD over half. Let's say mismatch is third RD. So one half is more and the other half is the other half is less. So we do it this way. The reason, of course, you can do it any way you want it, but this will make your equation a little bit balanced. And eventually, of course, the equation will look very easier to use because the way that you made the assumption. If you make a different assumption, the equation will look different, but the reality is going to be the same. And then we're going to see here is that we owe, let's call it we owe is going to be equal to I times R d1 minus RD2 times I times RD1, right? So RD2, RD1, actually, it's going to be we look at VD2 equal to VDD minus RD times RD2 times ID, right? So we're going to say, okay, so this is going to be RD1, this is going to be RD2. So then we can apply this current to RD D1, RD2, okay, RD1, yeah, plus, and RD2 is RD plus minus. And then the RD that is going to cancel, so eventually this just really equal to I times that RD. So that's what you have if you actually before we apply this is actually before we apply this voltage. Before we apply, just assume there's a difference between these two, and if we assume the current is the same, and this is going to be the mismatch, and this mismatch, as we illustrate, it can be balanced by applying a voltage at the input. So we apply the voltage over here, the positive here, negative here. So this is going to be positive half, and this is going to be negative half. So that's how we're going to resolve the problem. So we're going to see that ID1 equal to minus GM. So because this is going to be like a half over here, and this is going to be so okay, so just like this, right? And we know that you for small signal model, you know this VGS equal to half VOS, and you know that the current is equal to GM times VGS, right? So these are the equations here, then we can apply here. We got this ID equal to basically that's the DC biasing current minus the actual current induced by this common mode input voltage. And similarly, you can write ID2. So one is more, less, the other is more, plus GM over 2. Okay. And then now you can find VO1 and VO2. VO2 equal to and this two, the idea is that VO equal to VO1 minus VO2 or VO2 minus VO1 equal to 0, right? So simply saying that we have these two equal to each other, And then once you do that, you can basically eliminate a lot of these things like RD and I and so on. Basically, we got the expression for VOS. So we found that VOS equal to I over 2 times GM. So we got this equation here. VOS equal to I over 2 times GM delta RD over RD. This I is actually the current in each branch, right? This current actually is total current. So this is current here. So each of them have half of the average current. And do you know what this number is? So we know that, I think if you guys remember how to calculate GM. GM equal to 2 times ID divided by VOV, right? So that's GM. So the ID, 2 times ID equal to I. So basically you get to I divided by VOV. So therefore we can plug in this I equal to GM times VOV. We can plug it in over here. So GM is going to cancel. We got VOV. Basically just equal to 2 VOV over 2. So we got this number here finally. So you can see the voltage that you apply at the input to remove the DC offset is proportional to the resistance mismatch and also VOV divided by 2. So VOV is a part of the transistor performance. Right? So if there's no mismatch, basically you don't have to do anything. So therefore, VOS is 0. But if there's a mismatch, you can use this one to calculate how much voltage you need to apply. You know, for example, if VOV, let's say, is 0.2, and this will be 0.1 altogether. And if your mismatch is 1%, so which means the VOS is like 1 millivolt. So it's not that bad, but it's not that small because sometimes think about it. Sometimes your input is just a few millivolts. And now you have to apply 1 millivolt at the to remove the DC offset. So that's quite significant. That's why that's important. Now, the mismatch sometimes doesn't just come from RD. It comes from like device mismatch. For example, this device could have a different WOL. Okay, 0.1%. It could also come from K. The K could be, say, 0.1% difference, right? What else it can happen? But quite a few things that can induce. But I mean, you can basically follow the same procedure to derive what you need for each one. And eventually, when you design the IC circuit, if in the experiment, it's easy. I'm simply apply a DC voltage between these two terminals and see if I get how much I get output. Until I get a 0 output, and then I know how much voltage I need to apply, right? But during the large IC design, you can't do an experiment on every single one. So what you need to do, you would estimate the mismatch between these two. And then you would start to calculate how much the DC off voltage you need to apply. Okay, you would like once you calculate mismatch for this one, you calculate mismatch for K, you calculate mismatch for whatever that comes in, you add them all together, that's your mismatch. Some of them may be positive, some of them may be negative. The positive and negative actually cancels each other, which is good for you. But if everything is positive, you simply add them. If everything is negative, you will also add them together. So this is what we call the DC offset. There's one problem in the homework that deals with DC offset. So I figured out that I should have talked about this last week, but I got really sick last week. And after I got home, I got like 101 degree. Slept for 2 days. So any questions? So apparently before the final exam, we're going to do a review similar to what we did like before this lecture. Just try to connect the dots. But I think, again,
guys, try to get this main line. So the very, very foundation for this class is the small signal model for BJT and MOSFETs. The pi model and the T model and each of these parameters. So what I would recommend you is to do a little table and draw the circuit and write the equation for each of the parameters in the circuit. You'll find it very useful when you do the exam because you don't have to, again, flip the book to find the equation. It will save you a lot of time. Because some of the problems really just knowing the GM, knowing the RPi, knowing the RE, and it will get just right straight to the solution and it takes you 2 minutes to finish it. But if you have to look through the book and find the equivalent circuit, to find the actual parameter, to find the equation, it might take you like 10 minutes, 15 minutes to do all the problems, right? So today we're going to start something interesting. I know you guys learn circuits, you guys at the 210, 310, and 330. I want to ask you, what is a capacitor? Two conductive plates, right? And then, yeah, so two conductive plates, they form a capacitor. What's in between the capacitor? Salt water? Okay, physically, what is, I mean, material-wise, yeah, it could be dielectric. If it's electrolyte, yeah, sometimes it could be liquid, sometimes it could be, yeah, matter, solid. What do you say? Space or voltage, but phenomenon-wise, what's inside, what's in between? Electric field. When you apply voltage, there's electric field. Yes, you're right. So a capacitor basically is this, and you got two, like, so you got two plates, and when no voltage applied, it's basically just two pieces of metal. But when you apply voltage, see what happens? Initially, the capacitor does not have anything, so therefore the current will try to start to flow from positive, to upper plate and to the bottom plate. It forms positive up, negative down, and it forms electric field in between. Once the voltage of the plates are the same as the supply voltage, current stop flowing. Okay? So the process is called charging the capacitor, and there's the current. There's the current during charging. But once the charging is complete, there's not going to be any current anymore. So this is the capacitor. So basically, if it's a DC, you only have current like this. Maybe, eventually some of this circuit, you'll see like a little bit, oops, shouldn't do that. Starting from, right. You might have a little bit of resistance in here to limit how much current you will charge. If you don't current, you apply voltage to a capacitor. In theory, you cannot do that because it's going to create a huge amount of current. So initially, there's current, and if I apply DC voltage, and it goes like this. Okay. Okay. So your voltage eventually goes there, and if you look at your current goes like this. Eventually go to zero. So that's your current. That's for DC. But what happens when you apply AC? When you apply AC signal at the capacitor, what happens? AC means it's something like V equal to Vm times sine omega t. In that case, how much current would you have in the circuit? You guys remember? Well, this goes back to the basic relation of conductors and capacitors. So for capacitors, it's equal to C dV over dt. And for inductors, this inductor voltage
is equal to L dIL over dt. But for capacitors, it's the voltage of capacitor derivative times C. And this is in the time domain. And in your circuit analysis, you know that time domain is very complex. So therefore, we convert them into so-called frequency domain. So we write this down really into what we use I equal to J omega C times V. That's how we write the relations. And further, and they instead of they simply just using this S equal to J omega. The reason is using S instead of J omega make it a little bit easier in control theory, because eventually you can replace S with J omega to convert it into frequency domain. So this is, I don't know what they call this, but this is frequency domain, this is time domain, and this is like control domain. So in the control domain, we always use S, but when from S to frequency domain is very easy. Simply replace S with J omega. And this J is J squared is equal to -1. So you guys probably know all this. So what really does this is that saying, okay, with the capacitor, you can do a lot of stuff. Like in this circuit, we apply a voltage across resistor and capacitor. So we want you to find the voltage across the capacitor. Basically, this is a voltage divider. So we can write equation like this. VI is equal to R times I plus C, like the voltage across VC. Okay, so this is I. And we know that VC in relation to current I, right? So we know that current is C over d omega dVC over dt, but this also can be written as C times J omega, all equal to J omega C. Also can be written as SC. C J omega VC, VC and VC. So which means VC equal to 1 over SC times I. And now we have this one, VI equal to RI plus 1 over SC times I equal to R plus 1 over SC times I. Now we have VC equal to 1 over SC times I, right? So equal to so 1 over SC. Basically, if we plug in I equal to here, we know that VC equal to 1 over SC R plus 1 over SC times VI. So that's what we want to get the equation for. We will plus this I, and then plug it in here, and we got this VC equal to all this. So now you see this is voltage divider. Now you guys understand. This is voltage drop on the capacitor. This is total impedance. This impedance of capacitor, and your voltage across the capacitor. So that's the impedance of capacitor divided by the total impedance times the input voltage, get your output voltage. So in this case, we can also get, if we want to get the gain, would be VO over VI equal to 1 over SC over R plus 1 over SC. And this can be also simplified to 1 over S plus S RC. And we got this. So you find this is interesting. The gain is a complex. Basically, we can take this complex number to get its magnitude, and also get its phase angle. So for now, let's focus on the magnitude. So let's focus on magnitude. So this A equal to be 1 over, and amplitude means S is equal to J omega. So we plug it in. So it's going to be square root 1 plus omega RC squared. So we got this gain to this. So this number is very interesting. If you guys look at it, if omega 0, what do you have the gain for? 1, which means omega 0 means it's DC. You see, for DC over time, the voltage is going to charge 100% on the capacitor, so that's why your output is 1. And when omega increases, apparently this number start to be less than 1. The more omega, the less, or the much less than 1. But when omega is infinity, like very, very big, what happens? Well, omega is very big, which means this term is so big that you can neglect this 1, because but this is infinity, so your output is 0. So if you look at it, we can draw the output, or we can draw the gain, which is the same thing. We can draw the A, or we can draw the V. Basically, it's like this. So if at some point, like this, what it means that below certain frequency, your gain is almost 1. At some point, it starts to decrease quite quickly. And that point, and we, in the future, we have a name. So this one is called 3 dB. Why is it called 3 dB? Because that's when this number equal to this number, and this bottom becomes square root of 2, and the whole thing back up becomes 0.707. And if you take logarithm of 7.07, that gives you 3 dB. 20 logarithm of this thing, that gives you 3 dB. Okay. So if you guys look at that diagram on top, have you ever thought about what this is about? You know, with the frequency, or this is frequency. You know, as the frequency low, pretty much everything goes through. As the frequency goes up and it started to decrease, and eventually it will get down really to 0. This is called a low pass. Low frequency gets pass, and a high frequency gets attenuated. That's called low pass. So if we want to get this is low pass, if we want to get a high pass, which means we want to, if the frequency is higher, we want to get more output. But frequency is low, we don't care. What would you do for the circuit there? Just switch capacitor and resistance position, right? If you switch them, you would simply get the position and you get that. So I'm not going to go through the step to derive it, but in this case, what you get is this. And so basically, like this. Usually we're talking about the amplitude. So basically at a low frequency, you know, in this case, for example, if it's a DC, what do you get? 0. Everything dropping on the capacitor. As the frequency increase, it will start to increase, and eventually it will get down to at some point. You know, when omega is big enough, you don't care anymore because that drop on the resistance is so small, right? So then you get enough output. Okay. So this is what you get for your so this is a high pass, yeah. Now of course, eventually, in our circuit design, we will find that we sometimes need low pass, sometimes we need high pass, sometimes we need band pass. So we design filters like this. We purposely design. Like if you know what you want, you design a filter to fit your needs. That's man-made. On purpose, we design filters like that. It turned out in all amplifiers, this is actually naturally what happened. At low frequency, it doesn't work very well. At high frequency, it doesn't work very well. It only works in the middle band. If you want to increase your band, it's like you want really for low frequency application, you have to select your very special transistor. If you don't work for very high frequency, you also have to select your transistor. Like you go online, DGK, you buy yourself, I'm going to design my amplifier circuit. You're going to have to specify what your working frequency. You can't just go buy anyone. Like the one you buy might work for 100 kilohertz, But if we wanted to design, say, some sort of the Wi-Fi stuff, and it works like the gigahertz, 2.4 gigahertz, right? So your device will never work because your device only works here, but your frequency is right over here. So what happens? You need to shift, you need to select a different device that works like here, okay? So, so we want to find out how our device respond to different frequencies. And if we look at the middle band, is what we look at so far. Now, you might actually question what is the middle band? Well, the middle band is relative, okay, depending on your application, okay? Everybody's middle band is different. Like for the 2.4 gigahertz, the 2.4 gigahertz is your middle band. But if I'm working on 60 hertz, the 60 hertz is my middle band, right? So it all depends on the application. There's no fixed data, but the device, any IC that you buy, or any IC that you design, would provide you with a certain operation that in the middle part, it works perfect, okay? It gives you the gain that you want. Everything we learned from chapter 5 all the way to chapter 9 works beautifully, no problem. But if you move out of your band, or if you move close even to the cutoff, like here, you're gonna say, oh my God, my performance start to decrease, and we'll see why. But these areas here, like we call this one, the low cutoff, the high cutoff, okay? And the drop is defined as a 3 dB. Again, 3 dB is 20 log 0.70, 0.707 is -3. So from here to here, it drops -3, and we call this 3 dB. So if this is 0, this is -3. It corresponding to 1/√2. Okay. And this is a beautiful number. Like, why is this 1/√2? Because if you look at the equation that we have, 1 plus j omega RC. Just take this example. And our A will become 1 plus omega RC squared, and take out this square root. Okay, so if omega equal to 1/RC, what happens? And we call this like omega h. Is omega h is 1/RC. What you get? The RC and RC cancel, you plug in, you get the whole thing is going to be √2. So A equal to 1/√2. I believe it's 0.707. If we take 20 log A, it's going to be -3 dB. And this is called body plot. And we use this quite often. Now, in our chapter 9, when we talk about CMRR, actually the book also talk about converting into dBs. We didn't do it, but I thought, we better do it here. So the reason doing this 20 log algorithm is to make stuff a little bit easier to plot, easier to understand, and really simplify our lives. So now, after introducing this, let's get back into our transistors and see why that we care, or what happened actually for the low and high frequency. So we're going to start to look at high frequency response. High frequency response typically caused by internal structure of the device. So let's look at a MOSFET as example. For MOSFET, you remember how we build a MOSFET. So we have, for N-type MOSFET, we have P-type substrate, which is silicon. And then we have this N-type wells that are dig out of this P substrate. And then on top of the substrate, we have silicon. And above silicon, we have metal. And of course, at the bottom, we have body, we have metal again also. And at the source and drain, We also have metal. So earlier in the beginning of the class, I asked you what is a capacitor. You guys told me it's between two metal plates. Well, now we have metals. Means there's a capacitor. Okay. So you can treat this like substrate. They're not metal, but pretty much similar. You can treat it as a metal. So which means if we treat this as a metal, see how many capacitors you're going to have. So between source and body, see there's a piece of metal here, and there's a big piece of conducting material. Therefore, you have capacitance between source and the body. And here, similarly, from drain to body, you have this. As you can see here, drain to body and source to body, these two are actually symmetrical. These two capacitance symmetrical. And then you have gate. Gate is metal. From a gate to like a body, you have a capacitance, but instead, because this closer, this metal, like this is closer, so we'll have this CGS instead. So this is CGS. You might have also G to B, but because this is a little bit far, so capacitance is smaller, so we can neglect it. So we count this as CGS. So now all of a sudden you have 1, 2, 3, you have four capacitance inside the device. Now there's another one I forgot to explain, is from gate to drain. From gate to drain, gate to source, source to body, and drain to body. Right? So you have four capacitance. Now you have four capacitance that we never talk about it before. The reason it was in the middle one. And this capacitance, those capacitance are so small that it does not impact our output at all. Now, if we move a little bit toward the high frequency, what happens? We move a little bit towards high frequency, which means the impedance of a C is 1 over omega C. And that's the impedance, right? So if we look at the very low frequency, it becomes like an open circuit. 1 over omega C is infinity. It's okay. No problem. It's open. We don't care. But when your frequency is very big, this 1 over omega C becomes something that you have to be careful to use it. I mean, if 1 over omega C is so big that it becomes 0 or close to 0, what happens? Which means you become all short circuit, your device will never work. There's no output because everything is shorted. Because it becomes a short circuit, right? So the idea is that how are we going to resolve this problem? Well, this is where we need to, that's why I want to review the small signal equivalent circuit. So now we need to get back to the small signal equivalent circuit. Because for large signal, for DC, all these competitors don't work because they're open. Who cares, right? For DC biasing, it's no problem. So only for small signal, it becomes more impactful. So therefore, we have to consider. So now we need to look at what is a small signal model. Okay. If I draw a small signal model for MOSFET, you might laugh. You might be laughing. It's so simple, right? Is this your small signal model? Yes, it's your small signal model. There's a VGS here, there's GM type VGS, there's RO. So very simple. Okay, now look at this small signal model and look at this. We have capacitance, we have 4 of them. We can connect all 4 of them somewhere in the circuit. Well, let's do the 2 easy ones. VGS, CGS. CGS is the capacitor between G and S. So what would you do? Okay, sorry. D. this D, and this S. So VGS, CGS means it's here. So we'll put CGS over here. And then we have CGD. CGD means it's the capacitor between gate and drain. Where's our gate? Our gate here, our drain here. So we put gate and drain. Now, these two are fairly easy to put. And actually, these two capacitors are the ones that we are most concerned. And then, of course, we have to put the other two. And the other one is CDB and CSB. Now, in this circuit, actually, we don't have a base. I mean, we don't have a body. So in order to plug that one, we have to put a body here somewhere. The body, let's say, it's a body is over here. Huh? Body, not body plot. The body of this device. The piece of sheet is called body. We don't usually plot body because normally we don't do this. The current flows from here to here, like from here to here, right? We only plot the top part. So now we have to plot the body. Okay, so once you have the body, you will find out all SB is source to body. So source to body, we have this one. Okay, and then from drain to body. So from drain to body, we get this. We got another two capacitors. And well, the issue is that once we have this capacitance, CGS, and this one here, we'll find that this will create additional voltage at the gate. The additional voltage is going to create additional current. So therefore, the original current over here is no longer accurate. Therefore, we're going to have another current, which is called, this is going to be GM times what's it called? What do you call it? Make sure the numbers are correct. Yeah, VBS. And this is a GM times VGS. And VBS is calculated here. So we got this circuit over here. Now, once we got the circuit, of course, if we can now apply an input like over here, and then we can get for output. Okay, so we apply input, we can get output. Now, the circuit itself is a little bit more complicated than before because we got all the capacitance here, but it's not that unsolvable. So what we're going to do is look at here. So we replot it here. Basically, this is the same circuit, just organized nicely. So we have VGS here, CGS here, the VBS, CSB here. And the only thing that you be careful is that the plus sign at the bottom, minus sign is at top. And here is GMB times VGS, and this GM times VGS. This GMB is not the same as GM. So this is current is caused by the voltage drop between source and body. And then you have this one here. So this we can write nodal equations. Basically, if you look at it, we have how many nodes? If you apply voltage over here, and this is your output VO, and you can see that you have one node right over here, and you have one node right over here, you have one node right over here. So basically, this is not an actual node because you got a voltage applied here. And if you have a resistance over here, and that becomes a node. So you can write three nodal equations. One on here, one on here, and one over here. And you got input resistance, and you can solve for the whole thing. You can get the relation between VO and VIN. So that process itself is doable. If you use Mathematica, you actually start typing, and you'll be able to do that. But that doesn't really, that's only mathematical. It doesn't really tells you what's called insights, like what exactly it means, or which one has the impact, which one actually I could basically take a less consideration of that circuit. So in order to do that, we found that CDB and CSB, they're relatively small. Relatively small means 1 over omega C is infinity. So therefore, this two becomes open circuit. If this becomes open circuit, this becomes also open circuit. Okay, because it's 0 times GMB is 0. And this is 0, this is open, this is open. So therefore, we have equivalent circuit, open, open, and open. So we now get a circuit like this. So we got a circuit like this. And you might say, wow, this circuit is really, truly simplified. So now if we apply voltage at the input and we get the output, it becomes fairly like straightforward, but still we have to do a little bit of manipulation. I mean, it's not that just one step, right? So what we're gonna do is, based on this circuit, we're gonna find out. We're gonna find out what we need to. So here we open this one, and we open this one, and we also open this one. Again, this again just nicely draw circuit from the previous slide. So if we apply a voltage input, and we should be able to get the output by doing some mathematical analysis, and we can try to do that. Let's do some math over here. Let's gonna apply V, and then we're gonna have VO. Actually, I'm gonna just as a step further, I'm gonna add RL over here. Just to make it more interesting. So once we do that, you will see that we have basically just two nodes, one node over here, one node over here. But actually, this is what I'm going to do. In order to make it a little bit straightforward, I'm going to add a resistor over here to represent the internal resistance of the input voltage. So now we're going to do a node analysis over here and a nodal analysis over here. So on node 1, we see that there's current going this way, the current coming this way, and the coming this way. So for node 1, we have current V in minus VGS divided by RSIG equal to, that's current going into that node, equal to VGS times SCGS is the current going down, and plus, now here of course we grounded. So VGS minus VO times C, SC times GD. So you guys follow me? We have current going in, which is V in minus VGS divided by RSIG. That's current going into the node. And then we have current coming out of the node, which is VGS times the impedance of this one, divided by impedance. And divided impedance is S over CGS. Right? So that's how you get the current in this branch. And plus the current going in this branch, which is VGS minus VO times or divided by the impedance of this capacitor. So that's the second term. So we got node 1. And then on node 2, what we can do is we have all the current going out. The current going this way, this way, this way, this way, and this way. So we can write node 2, and then we have one current coming out that way is VO minus VGS times S CGD plus GM times VGS, that's one current, plus VGS divided by RO plus VGS SCDB plus VO, no, this is not VGS, this is VO. Okay, so we have four currents. Current coming out with CGD, which is the voltage difference between VO minus VGS times divided by impedance, and we have current of GM times VGS, and then we have current of VO divided by RO, and then we have current VO divided by CDB impedance, and then we have VO divided by RL. So we got these two equations. So within these two equations, we got variable VGS variable, and VO is a variable. So you have two variables. We can easily manipulate the equations and finally find the relation between VO and VGS. So if you find that, you can find the gain, which is equal to VO over VGS. Or in this case, it's going to be, again, also a complex function. And then we can have, actually not VGS, should be between the VIG. VSIG is the input. So we should do that. So we can get this. The actual equation will be very complex because the way that we do the manipulations. But so the book tells you that, well, we had a VDB there, but sometimes actually VDB is also quite small. So in fact, if you neglect VDB, CDB, it won't impact too much of the calculation. So we neglect it. If we neglect it, we got this one here. It becomes simpler like this. Even circuit is simpler like this, we still have to write the node equations or loop equations, to actually solve for the final answer. So what we did is this. Instead, we're going to do one thing before we move on. Is let's find the frequency characteristics. In order to find the frequency characteristics, the easy way is to find what we call a short circuit gain. So instead of voltage gain, we'll look at short circuit gain. The frequency response for short circuit gain and current gain, short circuit current gain, and open circuit voltage gain is the same. The frequency response is the same. So because it's easier to find the frequency response for short circuit current gain, so let's do that. So short circuit, it means we apply an input current. We apply current at the input, and then we short the output. So once we short the output, we find how much current is over here. And then we take the ratio between IO and II, and we got the relation. Now, so one thing you might notice already, if you short the circuit, how much current is in RO? 0. So that one can be basically taken out. So that is 0. So therefore we have now the first step is we can find VGS. So you guys see the current coming in, into here. But of course, there's a node here. So not 100% current is coming this way. So there's current coming this way, the current coming that way. So we will have to be careful, it's this way. So instead of writing VGS, actually, let me write down to a different way to express it. So let's write down II go to VGS times C S C GS, which is current this way, plus VGS minus VO times SCGD. So we write this equation like this. We write II, which is current this way and current this way. Okay, now we write the current on this side. So you guys see we can write IO. You can see IO is equal to the current this way and current this way. So we have GM times VGS and plus VO minus VGS okay. So we have these two equations. So as you can see from these two equations, this has IO as a function of VGS, and VGS is a function of II. So therefore, we can replace VGS as a function of II, and we plug in here, we should get IO, and we can get the relations. So from 1 and 2. So from 1, we can have so what we owe is zeros, right? So this is 0. So therefore, from 1 we have II equal to VGS SCGS plus SCGD. So therefore, VGS equal to 1 over SCGS plus CGD times II. So we got this one, and now we're plugging this one to here. Again, this is 0. So we have IO equal to GM plus, actually becomes minus from 2. So from 2, we have GM minus SCGD times VGS. And now we plug in VGS on here. We got GM minus SCGD divided by SCGS plus CGD times II. So we got this, right? IO. Now we can have the gain of AI equal to GM minus SCGD divided by S times CGS plus CGD. So usually GM is much larger than SCGD. So this number, GM, is much larger than this one. So therefore, that equation, the second term of our terms, you can basically just neglect it, and you can really I is equal to that simple equation. Let me write this down on the next slide. So we got AI equal to GM minus SCGD divided by SCGD plus CGS equal to GM or SCGD plus CGS. So from here, you can see that your current gain is basically proportional to, or inversely proportional to the CGD plus CGS and times omega. So basically this goes to AI equal to GM divided by omega CGD plus CGS. And if we take omega t equal to omega, this is an important step here is we define a frequency called omega t, equal to GM over CGD plus CGS. If this one is here, and we plug in this one back into this equation, we say omega t. If omega t is here, we plug in back to here, what do you get? Omega t, replace omega with this omega t, you got this one equal to 1. And this is called unity gain. Unity gain frequency. So what really does it say that if you got all this happening, but then you have your, at this frequency, your gain is 1. Your gain is 1 means your input and output is the same. So remember from all the way that we derived the middle band gain, well, we have GM times RD, right? So that's your actually middle band gain. So your middle band gain is your middle band. But when you have a capacitance in it, your gain is going to start actually to drop. At some point, your gain approaches 1. That's called your unit gain. So that's your gain in the middle band, you start to drop. And the unit gain is very important because at that point, your gain is already 1. And you further increase frequency, what happens? You further increase frequency, your gain further decrease. And your amplifier is no longer working properly because your gain is now too small. So we want to identify this unity gain frequency called omega t. And of course, from omega t, you can get ft is equal to basically omega t over 2 pi. So that's your unity gain frequency. And once we get to the devices, and we often would ask you, okay, given that these device parameters, find the unit frequency, unity gain frequency of that device. So it's a very simple equation. The idea is that you know how we got here, the process to get here. Now, apparently, in the exam, in the quizzes, you just have to find the frequency and know how to use these equations. Right. So let's take a 5 minutes break, and then we'll come back at 5:15, and we'll continue to finish the lecture.
Okay, let's continue. Yeah, again, really appreciate you guys here. The smaller class is actually not bad. You guys can hopefully, get more out of this. One thing I don't understand is we constantly have students missing the quizzes. I don't, I'm not sure what I can do to help them. But, taking the quizzes is one of the, at least you want to pass the class, that's something you need to do. Anyway, so having this unit gain frequency, knowing this is important because that's the point your gain started to get down to so low that you want to stop it. So this is important to know. Well, what is the frequency? Like for any given device, is it like hertz, kilohertz, megahertz, gigahertz? Well, if you look at the example in the book, and this frequency is typically in the gigahertz range. So you might say, well, okay, so far you talk about it, and then if I'm working on my frequency in the megahertz, I don't have to worry about it. That is partially true. Actually, most of the devices, the unit frequency is something like in the tens of gigahertz. Okay, and then you can get a better device even in the hundreds of gigahertz, but the higher like the response and the more expensive the device will become. So this is what we have with our MOSFET. And then for BJT, the structure is a little bit simpler. So therefore, if you recall the structure, the device structure of a BJT, you got N-type, P-type, and N-type, so NPN, right? So you got a 3 only piece, which means the maximum you would have are 3 capacitance. So basically, you would have is the capacitance between this, and between this. And because the base is in the middle, the collector and the emitter are separated by the base in the middle. Therefore, this capacitance is typically small, often can be neglected. So we're often only looking at this two, right? So basically, I mean, if you look at the device structure, you got kind of this, right? So you got this and you got this. So basically, we're looking at the capacitance between this one here and between this one here, right? And then, of course, you have capacitance between this one and that one is so far that that can be neglected. So we have here. Now moving on to a small signal model of a BJT, the only difference between this one and the MOSFET is that you have a RPi. The MOSFET is open circuit, but it doesn't matter. With this circuit, we can start to add these capacitors into the circuit. So if you look at, for example, this capacitor over here is between base and emitter. So between base and emitter, so we'll simply add it here. And this is between base and collector. So between base and collector, we add it here. And you have one from collector to emitter. So collector emitter, we add it here. So you can add 3 capacitors easily. Okay. So that's what you can add. Now, of course, here we often have to also add, now we have to add RO, because when you look at frequency response, you got to add RO because RO becomes such a, because C is already becoming important. So therefore, R becomes also important. So we got this whole circuit over here. If you look at this circuit, you might already notice that the only difference between this one and the MOSFET is the RPi. Really, that's the only difference. So which means we can use the same procedure to derive the gain between output and input and so on. But similarly, we should be able also to find out the short circuit gain. We can do the same thing. So basically, we're going to short this output. We're going to apply an input current over here. Now, the only difference again is become RPi is added, right? So what we're doing is, okay, so we're gonna, again, as I said, we normally would be able to neglect the capacitance between collector and emitter because that's a little bit too far, two pieces. We can neglect it. So now with this circuit, we can either write a nodal equation over here and here, or we can simply like write the whole thing. But what we want to do is to find out the short circuit gain, short circuit current gain. So to find the short circuit current gain, we'll need to apply current over here. And then we're gonna ground here. We're gonna also ground here. So once we ground it, we'll find this IO. So similar to the previous one, we can write nodal equations right over here. Or another equation right over here. Okay. So for node 1, for node 2, for node 1, we have current II coming in. Then we have two current coming out. One is current coming from, we actually have three current coming out. So one is, well, we actually have to assume some sort of voltage, V pi. So V pi divided by R pi plus V pi times 1 over omega or S C pi plus V pi minus 0 divided by 1 over S C mu. So that's code number 1. So from here we get II equal to V pi over 1 over R pi plus omega, or let's use C constantly, not using omega anymore. So we're going to use C S C pi plus S C mu. So we got this, which means V pi equal to this 1 over this whole thing plus S C pi plus S C mu, and then times RI. So that's node number 1. For node number 2, we have IO basically, this current over here is 0. So we have IO equal to just GM times V pi, and then plus, or plus, that's 0 minus V pi times S C mu. So equal to GM minus V pi minus, that's S C mu times V pi. So now we plug in number 2, 1 to number 2. We'll have IO equal to GM minus SC mu over 1 over R pi plus SC pi plus SC mu times I. So you can see this equation pretty much the same as what we got from before, except you got 1 over R pi extra term as a denominator. And the top is very similar with GM minus SC mu. The other one is S minus C CGS. So this term basically often can be neglected because it's very small. So we got the bottom is instead of 1 plus this, we got 1 over R pi plus this one. So over here, we can, what we can do is we can find this so-called beta, because beta equal to IC over IB. And what I found initially I called IO, basically semi-IC. So if you look at here, I basically equal to IB, this IC, this IB, so IC over IB equal to this. So basically equal to GM minus SC mu over 1 over R pi plus SC mu plus C pi. So that's kind of a beta. So if we can neglect this one, and then at the bottom,
do you see what happens? If S is very small, if S is very small, what happens? It means this is small, neglected. S small, neglected. What do you get? GM over 1 over R pi with GM times I pi. That is exactly the middle band again, right? So this is exactly what omega is small, S is small, this beta equal to GM times divided by R pi. That's exactly your middle band again. But when S is not so small, you can no longer neglect this S or this omegas, your beta start to decrease. So basically, if you look at your beta, if you look at this, your beta, it goes like this. It goes like, okay. And at some point, it started to decrease, 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 decrease. And here, if we use dB0 means your gain is 1. So log 1 is 0. So therefore, that's called 0. 0 is called unit gain. So similarly, can you guys write together what is unit gain frequency here? Well, basically, unit gain frequency means that if we neglect this one, we will simply just have this one equal to 1. Right? So that's unit gain. And from that to 1, you can find what your S is. And by simply, so basically what we're doing is we use Gn over 1 over R pi plus omega C mu plus C pi. We take that equal to 1. And then find this omega t. And you can find this omega t is equal to basically GM So basically, we if we let me do one step further. Yeah, let's do one step further. Is if I multiply R pi on both of this, so I would have GM times R pi over 1 plus omega t C mu plus C pi times R pi. So that's what we have equal to 1, and then you can find WT over here. But in general, if WT equal to 1 over C mu plus C pi Yeah. So if we have WT equal to this, we're plugging this one into here, you see what we get? So this term becomes 1. So this becomes 1 plus 1. And GM R pi, of course, there's J omega. So basically we have to put this J omega. Okay, so just put J omega. So this is going to be like a complex number. So the absolute value or magnitude becomes 1 over 1 plus J1. So it's square root of 2. So the whole thing becomes, gain becomes if, and then gain becomes, the beta becomes 1 over square root of 2. So instead of getting to 1, of course you can always get that value, but instead we got this beta at this point, we got this number, and this number is called a 3 dB frequency for that. Yeah.
You keep the J omega in the denominator. Why do you get rid of it in the numerator?
We
Let on your Durand beta. That one.
this one?
Yeah.
Did we? Well, no, we did not get rid of denominator. I mean, oh, you mean GM? GM times R pi. So this is better. This is a constant. So this becomes beta. Oh, well, let's call it beta 0. Yeah, so this term is better, right? So basically I multiply r pi to the top, so I get 1 plus pi times this one, this will become gm times r pi. I only got rid of this because this is small, I neglect it. Yeah, so this is better, and then, well, you know, it doesn't always have to be 1. So let's continue. Don't call it 1. Let's call it just beta. So this becomes better and this better. The top is beta 0. And then if omega t is this much, we plug it in. We got beta equal to beta 0 divided by the square root of 2, which is 0.07 beta 0, right? So let's just do that. So which means if omega t is less than that number, oops. Oh, interesting. Okay. So basically what it says that if we take that beta 0 over 1 plus r pi omega times c mu plus c pi, and we take that and we do 20 log, and we take the number, and then we also put this beta 0, actually we put the beta 0 out instead to make it easier. So we put this here and we multiply this one by beta 0. And we got this. So if we take this, you can see that when this number is small, basically the whole thing becomes like 1 on this. And then this is really just beta 0 at the beginning. And then it would go down at omega t. Oh no, actually this is omega beta, not omega t. Okay, omega beta, we call it omega beta, or here it's omega beta. I have to go to my previous slide to correct it. Sorry about that. So this is omega beta. Yeah. So when at this point you get a 3 dB. So if omega beta, let's see, omega beta equal to 1 over c mu plus c pi times r pi. And you plug this into here, that whole thing becomes 20 log minus 3 times like beta 0. So beta 0. So what we're drawing here is right over here. So, and then beyond this one, it will go like as a line going down. Because what happens is that why this becomes a straight line? Because when omega is big enough, this term is so large that, because if this is 10 times larger than 1, so in body plot, we said that we can neglect this one. So if this is larger than 1, we neglect this one, you see what happens is this whole thing is inversely linear proportional to omega. So which means for every like 10 times decrease, this line is going to drop 20 dB. So this x is logarithm. It's not linear. It's logarithm. So when omega change from let's say from 10 to 100, and this would drop from let's say 0 dB to minus 20 dB. So that's why it's called minus 20 dB per decade drop. So basically, this is all becomes, maybe do it this way. So 20 log something that's called beta. Okay. So if beta equal to 0.1, you got minus 20 dB. If beta is equal to 1, you got 0 dB. If beta is 10, you got 20 dB. If beta is 100, you got so for the logarithm, the beautiful logarithm is that for every 10 times increase, the decibels change 20. So that's by definition, logarithm. So in this plot, basically you look at it is when we have between when beta is actually above a certain level, when omega is small enough, the whole thing can be neglected. So therefore, your 20 log 1, basically, well, if I move beta 0 out, it's not nice, because it should have been beta 0 here. So basically, that's whatever you get again for the middle band. That's whatever gain you get the middle band. So let's move the beta 0 inside, because otherwise it's gonna look problematic. Right. So we get better 0 if omega is small. If omega is small, then gain is basically 20 log beta 0. When omega is large, very large, and the gain becomes 20 log omega times the whole number over here. So basically, you see omega, every time omega increase 10 times, your gain decreased by 20 dB. So that's what it happened. And that's how we plot this one. And we found that at some point, it's going to cross this one. It's called 0 dB or unit gain. So this is corresponding to basically the gain is equal to this thing equal to 1. And I think what we get from the book, we get WT, okay. So basically it's WT over equal to beta 0 times omega beta. So this is your gain over here. Okay. So one of the things that sometimes I want to like illustrate some even useful information is look at this beta and compare to okay. So if I do this one and I like let this omega beta equal to 1 over r pi times c pi plus c mu. So I let omega t equal to this, and this is r pi is over here. And then we get beta equal to beta 0 plus 1 plus we got beta t equal to gm over c mu plus c pi. Omega beta is actually, so this is equivalent to 1. So this is approximately 1, because this is really just beta is, because beta is, generally, remember beta 0 is what we use beta in the beginning. It's about 100. So 100 over 100 over 1 is approximately 1. So this is why we call it unit gain. Unit gain. And the frequency for unit gain is W beta is WT over beta 0 times omega beta. So that's what we get for this BJT. So it's slightly different because in the BJT, you don't have this beta 0 things like that. It's mostly just that. It was a CGS plus CGD. But here you got this beta and times omega pi. So there is a slight difference because the introduction of R pi. And if we look at examples in the book, it will tell you that the gain, the unit frequency is somewhere around like 7 gigahertz and 130 megahertz, the different devices. But for MOSFET, it was in the tens of gigahertz. So this apparently BJT is typically 10 times or even 100 times not as well as MOSFET for high frequency. The frequency band is much shorter for BJTs than MOSFETs. So that's the intrinsic property of this. So basically, if you look at typical in the future, in this whole chapter, throughout, we're going to use this body plot to look at the frequency response. So in this case, basically what we're doing is using simplified circuit to illustrate how the output is impacted by frequency. So in this case, you see what we have in the input divided by R and C. So the RC is a low pass filter. We already illustrated in the beginning. On this side, we have output, which is equal to, we always go to just, R times these two resistor and capacitor in parallel. And by doing this, which is really just a low pass filter, and you got this output, we can derive. We probably don't have time to derive it here, but we could if we want to, because we always go to minus VI over R, which is the current over here. No, actually, this is not correct. VI over R plus S 1 over S C. That's the input. Then multiplied by R. Oh, okay, I see. I don't know where I got this equation. So they got R over here too. They got R over here, and then that's R. That's not right. We shouldn't do that. But typically, what happens is that, let me actually don't do this, just not to confuse you guys. So we got a voltage as a function of input. That's what you have. And then we can have gain equal to VO over VI, which typically is a function of omega or function of S, whatever you want to express it. And then we can take the gain is going to be, just take the whole magnitude of A, and then we multiply by this by 20. We take the logarithm. We take 20, so this 20 logarithm VO over VI. And this is a function of omega. So, and then we plot it. We plot this thing as a function of omega. And so over here, you can see we go from like logarithm from certain frequency, and at some frequency, this thing is going to start to drop. This called like a decade. So between every time increase by 10 times, it's called a decade. And at this point, so at this point, the expression is like 1 over square root of 3. So this is 20 over 1 over square root of 2. So that gives you minus 3 dB. Right? So that's why if you look at here, this point from the horizontal line, it drops by 3 dB. So that's called a 3 dB frequency. That's some point you'll get this. But if you go down 10 times lower than the 3 dB frequency, if you take the logarithm, you will find that this almost close to like the 1. Okay. And then if you increase by frequency by 10 times from the 3 dB frequency, you'll find that everything, it goes like linearly. It goes linearly every 10 times. Okay. And it drops by 20 dB. So from here to here, it drops by 20 dB. So the blue line is approximation. And the black line is, the black line is approximation, and the blue line is actual curve. So when you are asked and sometimes say, draw the body plot, you don't have to draw the blue line. You simply draw the black line. So here is approximation basically, but this actually, there's a 3 dB drop. We all know about it. We don't know it, but we put this in black line. So this is with 1 omega at the bottom, like so far we have discussed. But if you have like 2 omegas, like omega squared, you know what happens? Yeah, you would double it. But see, the way to double it is to look at if the bottom, like so far we have, is always something like 1 over 1 plus S over omega, let's call it omega h. That's what we have. But if you have S squared at the bottom, you would be able to decompose this one into something like 1 plus S omega h1 times 1 plus S over omega h2. Now, this omega h1, omega h2 can be the same, or it doesn't have to be the same. If they are the same, you see what happens on this diagram, which means your 3 dB is actually over here, but your line start to drop instead of 20 dB, it's going to drop 40 dB every decade. Why? This is omega squared. The squared means you take logarithm, the square becomes 2y. So it becomes 40 times log 1 over omega. Therefore, for every 10 times drop, this slope becomes 40 dB instead of 20 dB. If these two frequencies are not the same, you see what happens? It might drop 20 dB over here, but it might drop over here. It depends on the other frequency. If the frequency exactly 10 times, your second line will start to drop 40 dB over here. So that doesn't have to be that way. So which means you could basically, at any point, you start to drop 40 dB. Okay, if you have 3S at the bottom, what happens? At some point, you can have minus 40 dB drop. So it's steeper and steeper and steeper. So, or in the future, you might see that, yes, for some amplifiers, we have 1 pole, but for some of them, we have 2 pole, 3 pole. And those frequencies are going to be different, like omega h1, omega h2, omega h3. You have 3 poles, and then the frequency will start to drop. The gain will start to drop 20 dB and 40 dB and 60 dB for the each. So now we want to move on to look at real amplifier. Let's just look at one of this, and we're gonna stop. So for a common source amplifier, we already had the equivalent circuit, and we derived the short circuit gain. Now we look at if we have a resistance at the load, and we also have a resistance, input resistance of the source, and see what happens. We want to find the gain, voltage gain now, and we want to plot the gain as a function of frequency, see what happens. So in order to do that, we need to draw the small signal equivalent circuit. So basically, we need to draw the circuit like this. We want to draw the the pi model. So we start to draw the pi model, and we have the capacitance over here, and we have. Here. Here. Right. So you see, when we have the equivalent circuit of the pi model, the initial pi model was a very simple open circuit. Now we added this. So from the previous study, you already know, like previous discussion today, you know that how to add these capacitors, and we have input and we have output. This is actually a very simple circuit. We can analyze this circuit very easily to find out the relation between VO and VSIG. So the way to do this actually is a little bit tricky because even though we can do it, but the expression would become quite complex. So let's move to do step by step. So we have RO and RL. So these two resistors basically are in parallel. So for one step, we can do this two together, RL over RO, parallel. We use one symbol called RL prime to represent these two resistors. So now we can write this nodal equations. And we can write a nodal equation over here and a nodal equation over here. So on the nodal equation over at the point 1, we have current coming in, current coming out, and current coming out. So we have VSIG minus VGS divided by RSIG, that's the current coming in, equal to VGS coming out times SCGS plus VGS minus VO times C SCGD. So that's the first equation we write on the left hand. 3 currents, current coming in, 2 currents coming out. And then next, we need to write the equation on the right hand. We also have, now once we combine these two, so we think there's one current coming this way, one current coming this way, and current coming this way. They have 3 currents. So we add them all together to get 0. So it's going to be VO minus VGS times SCGD, which is the current going from right to left on CGD, and then plus the current going down, which is GM times VGS, and then plus current of VO divided by RL prime. And then this RL prime is given here. So we have 2 equations here. So from equation 1, we can find out there's one VO, there's one VGS variable, and here we have VO and also VGS variable. So definitely we will be able to find the VO as a function of basically VSIG, because what we want to eliminate is VGS, and then we find VO. To do this, it's just a little bit tricky because it's going to be kind of so it's a little bit kind of difficult to derive the actual expression. So I opted to skip that. Instead, we're going to simplify the circuit. So if our simplification in such a way that it does not impact the actual numbers, like it becomes 1,000 to 999, really who cares, right? So that's what we're going to do. So the idea to simplify this is that this voltage here, VO, in fact, because the current here is so small, the current here is so small, so VO is pretty much this voltage times this resistance. So that's the assumption. And in reality, it is actually true because this current is like in milliamp and this is in microamps. So it's about 1,000 times the difference. So therefore, VO is actually approximately minus GM VGS So we found that yes, VO is pretty much this number, just this, neglect this current in the CGD. So if you do that, if you go back to our previous equation, you find, okay, if we find VO is equal to that, and we would simply replace VO in this equation, and we find that, well, there's GM times VGS times the RL prime, right? R prime cancel, we got this cancel. So we get actually this equation, this one equal to, oh, plus, what is it? Oh, equal to 0. So I forgot that equal to 0 sign, right? So so we plug in that, and then we found that now we can write IGD which is the current over here. IGD is the current going through VGD. Now, since we said we always approximate that, so we plug in that we over here, we got IGD expression. So basically, it becomes VGS plus GM VGS RL prime times SCGD. And we have this one is 1 plus GM RL prime times SCGD times VGS. So the idea is that if we assume IO, then we will be able to find IGD, which is current over here. Now you might ask, okay, now you say you can neglect IGD. Why you are calculating IGD? What are you doing? What are we doing, right? Well, the thing that IGD is small in comparison to the load current. So on the output side, yes, we can neglect it. But on the input side, the gate current is very small. You can not neglect it. That's why we're calculating it. We're adding it back to the gate current. You see what I mean? It's like, how do you make a comparison, like analogy? It's like, yeah, more just by numbers. Let's say the input is 1 microamps. IGD by calculation is also 1 microamps. You cannot neglect it because 1 plus 1 is 2, right? But the output, your output is 1 milliamp, and then your IGD is 1 milliamps, 1 microamps. So 1 milliamp minus 1 micro is like 999. So therefore, I can neglect an output but not input, right? So maybe comparison to a rich man and a poor man. Like a rich man, like $1 billion, give him $1, I don't care. But the poor man has $1 to can buy bread, right? He has only $1, you give him $1, you can buy 1.99, you can buy bread. But you give $1 to the billionaire, he doesn't care, right? It doesn't change it, right? So that's probably a good comparison analogy, right? So now we find IGD. So once we find IGD, is that okay? So we'll say this IGD is. I think we want to use some sort of numbers here. So S1 plus GM RL prime times CGD times VGS, and we're going to use SCEQ times VGS, and this CEQ equal to 1 plus GM RL prime times CGD. So we find this, just use this CEQ to represent the long expression. So we find IGD. And this, okay, so the next point that we find IGD, and we found that this current out here and the current out here, and we found our current here is a function of VGS. So if you look at here, this IGD, what do you see this equation, like this equation here? What do you think it look like, right? So this IGD means VGS, which means this is going to look like capacitance to ground, and this is CEQ, and this voltage is, does it make sense? The VGS times SCEQ, so VGS times SCEQ gives you current. So that's IGD. So that is what we have for the whole thing that we, up to this point, we said, well, this IGD is just equal to this, which means now we can basically redraw this circuit. Instead of drawing CGD in V10, we draw this. So we're going to draw okay, so this is CEQ, and this is CGS, this R SIG, and this R prime. Do you see what I get? Because this IGD is equal to this. Therefore, I use CEQ to be put it here. Doing this is so significant because I basically separate this two circuits. By separating two circuits, I can simply use this as a voltage divider, and I can calculate voltage basically on this one. So this is so beautiful by doing this is that, okay, so for equivalent CQ, yeah. So this is equivalent circuit that we have found. Basically, I separate this circuit, and I show you already how we get this CEQ. So by doing this, I can have voltage divider over here, and I have current voltage over here. So let's do it. This becomes so simple because I got VGS equal to VSIG. The voltage divider means this is a, well, these two capacitors in parallel, right? You can add them. Okay, parallel capacitor, you add them. Like resistance in series, we add them, parallel in everything. So we basically add like 1 over SC EQ plus CSG. And bottom we have RSIG plus 1 over S times C EQ plus CSG. That's VGS. We got VGS right now. And then next step will be we write VO equal to minus GM times VGS times RL prime. And then we'll simply plug in this one to here. We'll get minus GM times RL prime times 1 over S CEQ plus CSG RSIG plus 1 over S CEQ plus CSG, very actually, and then times VSIG. So now we can get gain equal to VO over VSIG, it's going to be GM times RL times this whole thing over here. I'm not going to rewrite it. It's just that same equation. So you guys look at this. This is actually so about, I need to get the minus sign over here. If omega is very small, what happens? You see, if omega is very small means this one No. Very big. This is very big, we can neglect this one. And then this and this will cancel. One over, what do you mean? Large number over large number, yeah. So one. One means GMRL prime. You see, GMRL? That's your middle band. So when frequency is low, you got a middle band. What happens when frequency is high? When frequency is high, that this gain started to change, and then your sense start to decrease. So what I want you to do is just to use some numbers, some symbols to represent this thing is 1 over yeah. So I'm gonna simplify this one by multiplying S C equals C pi on bottom and the top. So we'll get 1, and then 1 plus RSIG times CEQ plus CSG and plus S. I'll put an S here. So yeah, so this is what we get on A. So now we can rewrite this one into further is minus GM times RL prime, and then times 1 plus S over omega H. I'm going to put everything. So you probably can tell me right away, what is the omega H, right? Is it 1 over R? Why is RSIG? No, this, yeah, RSIG times CEQ plus CGS. So this omega H is called what's the name called? It's the 3 dB frequency, because if omega H, you plug in omega H into this equation, what do you get? S omega H, you get 1. So 1 plus J omega 1. And the whole thing becomes 1 over square root of 2 if you take the magnitude. So 1 square root of 2, you take the 20 dB, you get minus 3. So that's what we call a 3 dB frequency. Okay, that's a 3 dB frequency. And if we plot this thing, let's see if I have, yeah. So if we plot this thing, you'll find that, well, below 3 dB, you really get what you have. And by increase at the 3 dB, you got this FH equal to basically omega H over 2 pi. Right? And then omega H, we've already found omega H is equal to that. So omega H is equal to 1 over RSIG times so that's what your FH, and then if you take 20 log, and then this is going to be like 20 log one plus omega. So this is what we have, 20 log. We simply just plug in the gain and get the 20 log over here. Apparently, I mean, here you can have your GM times RL prime over there, but you don't have it here, but that's okay. We typically take that out because that's your like middle band gain. So we just simply do this. Now it's much clearer. So if omega is omega H, you get this is a minus 3. If omega, so let's say, if omega is 0.1 omega H, what do you have? I don't know what we call this. So if omega is, let's call this gain. So if omega is 0.1 omega H, over here, omega is 0.1 omega H, means that's 0.1. 0.1 squared is 0.01. So the 1 plus 0.1 is 1.01. and square root of 1.01 is approximately 1, and 1 divided by 1 is 1, log of 1 is 0. So you get basically gain is 0 dB. That's why you have it here, 0 dB. Okay. Now what happens if omega is, we already said, if omega h, you get minus 3 dB because, again, what to do again? So 1 omega h is 1, so 1 plus 1 is 2, square root of 2 is 1.4, 1.4, 0.77, 707, 20 log this one times 20 gives minus 3. Okay. What happens if omega is equal to 10 times omega h? Time is 10 over omega h is 10. So 10 squared is 100. 100 plus 1 is 101. Square root 101 equal to almost 10. Okay, 1 over 10, 0.1, log 0.1 minus 1. Minus 1 times 20, minus 20 dB. Okay, so similarly, if omega is 100, omega h, what happens? And we don't have to do it. So you guys know it. How many dB do you think? Minus 40, right? Because 100 over 1 is 100, 100 squared plus 1 is 100 squared, square root is 100. 1 over 100, 0.01. Log 0.01 is minus 2. Minus 2 times 20 is minus 40. So minus 40 dB. So that's why you see, that's probably better to explain now why it's 20, why it's called 20 dB per decade. Because for every increase of frequency by 10 times, your dB dropped by 20. So that's why we call it minus 20 dB per decade. So from here to here is 20 dB, and from here to here 20 dB, 20 dB. So it just keep dropping. Every time it's going to drop 20 dB. Of course, you know, what we're concerned is that this is a region that it's good for us, but this is already not good. By this time, we think, oh no, it's already dropped too much, right? By this time, it's not usable. By this time, it's garbage, right? So we basically are interested looking at what happened in this area, okay? So this is a kind of a very interesting phenomena, and I think we probably should, or we're already over time. So we will stop here, and then next week, the quiz. You guys probably interested to know about this. So the quiz next week basically is going to cover what we cover today in chapter 10 only. So nothing in chapter 9. So chapter 10, basically you're looking at the unit gain frequency, okay? And don't mix omega and the f. There's 2 pi difference, right? So when you do your problem, you know, sometimes you forget to divide by 2 pi. And then we're going to look at basically common emitter, common source amplifier to look at this type of stuff, you know, look at why we got this 20 dB stuff. So this, hopefully you guys really got a good handle on this, and should be doing well next time on the quiz. Okay. Any questions? Yeah. What is it? What did I do? Negative? Oh, -3. When you put the 1, so yeah, 1 plus 1, you know, omega is omega h. I mean, omega h, this becomes 1. So 1 plus 1 is 2, right? Square root of 2 and 0.07, 1 over 0.0, I mean 1.141, right? And then 1 divide that and take a log, and then multiply 20, you get -3. Okay. Okay. Have a good night. Have a good weekend. Sure, no problem. Give me 1 second.